So just a quick recap of what I mentioned at the beginning of the lecture. Working with ultrasonic testing, we're going to be in a high frequency range. So audio frequencies, audible frequencies from about 20 hertz to 20,000 hertz is what humans can typically hear. Infrasound is anything below that. Show the vibrations of an elephant walking by. Ultrasound, we're usually going to be somewhere in the 50 to 100 kilohertz up to about 25 megahertz range. And so that's what our testers are going to be running, and you're going to have to set that frequency as part of your testing process. Okay. Different probes are designed to work with different frequencies. So some testers allow you to set it, others don't. Just kind of a quick review of, or kind of how these work. The elements inside of our probes most of them are piezoelectric, which means they are a semiconductor crystal that can convert mechanical energy into electrical energy, so mechanical vibrations into electrical pulses, or they can convert electrical energy in the form of alternating current into a mechanical wave or an ultrasonic wave. So the mechanical vibration and electrical voltage have the same frequency, right? The frequency is the same. The amplitude obviously will vary. And there's, some of the different materials they're made out of: quartz, lithium sulfate, barium titanate. Most testers today are going to be the barium titanate. And so, but the material doesn't matter as much. You just need to know the properties of your probe. What frequencies it can be run at, what size, what kind of materials it's designed to test. So we take these piezoelectric crystals and we mount them inside of our probe or our transceiver. So you can see it here. Here's the element right here. It's got its two electrodes, top and bottom. Okay. There's going to be some kind of a backing material. The backing material is a very dense material. And the idea by that is we want the energy produced by that to primarily go, in this case, down rather than up. And so by putting a dense backing material, that's going to reflect most of the energy down, right? Any vibration that hits that's going to hit it and bounce down along with whatever energy is going already in that downward direction. It's potted inside of a like an epoxy compound, just to kind of hold everything together and also to protect it from shock, like if you were to drop it or that kind of thing. Wiring runs up out to your tester, and then on the face, you're going to have a wear plate right here, because the crystal itself, you don't want to be rubbing that against metals or other semi-abrasive materials. And so that wear plate typically is made of some kind of a metal. Usually it's like a steel. It can be an aluminum, but typically it's a fairly hard metal so that it wears well. And what that means, though, is that the signal is being generated and received if it's a transmit-receive motion, or if you've got two of these, one's a transmitter, the other one's a receiver. There's going to be a slight difference from the actual crystal to our part, right? Our part, or the material we're testing, is going to be on the other side of that wear plate. And so we get, there is a slight offset that we have to take into account. So one of the items you have to set as part of your calibration setup process is the offset to take into account that very small difference between where the crystal is and where the front face of your part begins. Now, every time we have a material interface, we get a reflection of sound. That also is going to attenuate the sound. It's going to reduce the amplitude of the ultrasonic wave. And so what we're going to use is something called an acoustic couplant, or we just refer to it as a couplant, to acoustically bind our probe that we have here, our transceiver, to the test piece, to the material. And so it eliminates any air. Air is a good insulator of sound, so the couplant fills in. You're always going to have that face, that wear plate, and the face of our part. You can even see there's grain structure on this part is not perfectly flat. And so we don't want to have all those little air pockets. All those little air pockets will attenuate the sound, make it so that we don't get as good of a signal. We'd have to turn our amplification up really high, and that would cause a lot of distortion, and it would cause a lot of interference that would make it hard to use. So we put this couplant here, and it acoustically bonds the two of them. It's a glycerol gel. Glycerol gels are used in things like it's the jelly type liquids. The one I bring up is KY jelly, is what probably most people are familiar with. That is a glycerol gel. This is the same basic kind of a compound. So it's inert. Most materials it won't affect. It's pretty safe to handle. It still leaves some residue. You can wear gloves and that kind of thing. Yes. Well, you're calibrating, so can it mess up the signal? If you had air pockets in there, that would mess the signal up even more. And so part of your setup of your tester is you're calibrating where that point is. You're going to set something called the offset, is where the zero offset is where the sound wave actually is entering the part. And any of that distance between, because yes, there's a thin layer of that gel in there, right? So anything that is above the surface of the part on our display screen, we're essentially going to shift the whole display and just put it off the side of the screen where you don't even see it. And so we take that into account as part of the setup process. When we put one of these on, so here the probe is on the left side, that you can look at that kind of that blue crystal, right? They're going to be designed and shaped in such a way that they focus the sound beam. So remember, you look at sound beams or sound waves, right? The typical sound wave is if you have a perfectly flat surface or flat, it's going to come out at a waveform that looks something like this, where it's expanding as you move further away. And so what they do oftentimes with these is it shows the crystal flat, but really the crystal is almost more dished, where it kind of drives that sound wave back together. But you can't make it perfectly, you can't make the two sides of it parallel. There's always going to be some angle there. So it kind of angles together till we get to what's called the focal point or focus. And then, it kind of comes together, and then, what was on the top kind of becomes the bottom. So this part of the beam is going to continue this direction. The bottom part of the beam is going to continue up to create this upper part of this actual cone in the far field. And the areas where we can accurately test is outside of that near field. There's a lot of interference here in the near field. So, you get a big, what's called initial pulse, that's going to obscure anything in the near field. And so this is where it's hard to use this. This technique is not really good for finding surface flaws. It's primarily going to be for subsurface flaws, because this focal point is going to be a certain distance below that crystal face. And then the actual acoustical area we can test is this far field area. And then you have what's called the angle. You can calculate the angle of divergence based on the frequency and that kind of thing. So we have to be aware that this will affect our tests. So in that near field, because you have all those waves kind of coming together and crossing up at the focal point, they're going to interfere with each other, and we can't get a clear indication. Now, what we can do, there are some probes that have what's called a delay line in them. It's a piece of acoustically transmitting material that's attached to the front of the probe that physically offsets it from the part, so that the near field falls in that delay line block before it enters the part. And those are used for finding more surface. We do have some delay probes if you want to try playing around with them. But you get the wave interference that I'll show you on a video here in the next slide. Once it gets into the far field, those waves become uniform again, like you would have here with the flat crystal. And it is going to spread out at that angle of divergence. But if it's not going to diverge as much as if you had a totally flat crystal, where you would just have the wave spreading from the get-go, right from the initial face there. So this is what's happening in that near field area. So because of that constructive and destructive interference taking place in the near field, that's considered a dead zone. It creates this dead zone that occurs in the near field. And so the immediate echo from the entry surface rings back to the transducer. You get that constructive and destructive interference in the near field. And so any flaws that end up in the near field, you're going to have a very difficult time being able to see. So again, we can either not use a probe to try to find it, right? We can switch to something like eddy current or dye penetrant to try to find surface flaws, or we can use what's called the delay line probe that offsets it, physically moves the ultrasonic probe away from the surface in order to see it. Here's another kind of representation of what the beam looks like coming out of one of these ultrasonic transducers. There's that near field showing all that interference taking place, and then the far field where you have more consistent kind of wave fronts, beam fronts that are used for testing. If we look at it with a probe that's on a part, it looks something like this, and now we can figure out, our near field length and the angle of divergence based on the properties of the sound that we're using. So near field, right, the distance of near field, this is the distance from the transducer face. And remember, this is the transducer face, so this part of this is going to occur in that wear plate area, right? It's going to be, it's not going to all necessarily, it's not going to be from the surface of the part, but you have to take into account how thick that wear plate is. The near field distance is equal to the diameter of the transducer squared times the frequency divided by 4 times the velocity of sound in a test material. So I'm going to give you something to try, and I want you to tell me how far this is. Anyone got near field area or distance? Not area, but distance, near field distance. So velocity of 5,100 meters, frequency of 1 megahertz, and diameter of 0.5 centimeters. Any takers? Nothing? You're very quiet today. Okay, our depth, what's that? No, not 0.0625. No, 5,000 to what? Yeah, it's 0.0012 centimeters. 0.0012 centimeters. Zero 0.0012 centimeters, which is 0.000012 meters. Right? Okay. So you can see it's not very far, but it is fairly, it is going to obscure a little bit of the surface. Okay, next one is the angle of divergence. So using the same example, velocity of 5,100 meters per second, frequency of 1 megahertz, diameter of our transducer 0.5 centimeters, velocity of the sound I've got there. What's our angle of divergence? And just a quick note on here, remember the angle of divergence is half of, is from the central axis, the acoustical axis, so straight down from the probe. So if you're trying to figure out the full width, it's going to be double that angle of divergence. Okay, but typically angle of divergence is taken from the acoustical axis to the edge of the wave. So velocity of 5,100 meters per second again, frequency of 1 megahertz, diameter of our probe 0.5 centimeters. What is our angle of divergence? Okay, so I heard it. So 1.224 degrees, which means the total angle or the total width of the of the wavefront would be 2.448 degrees. Okay, because it's going from that acoustical axis. Quick reminder of longitudinal versus shear waves. Okay, longitudinal showing on the top right here. That's that compression and rarefaction taking place. The shear wave shown at the bottom is what we think of, what most people think of as a wave if you look out at a, look out at a pond or a lake when you throw a rock in it. But remember, primarily we're going to use for straight beam, which is what we're going to be conducting and what's used most often in aviation, we're going to be using the longitudinal wave property of sound in a material. Okay. So it looks something like this, unless we're doing angle beam. To angle beam testing, we look at the shear wave side of it. So here's a probe on the left side doing pulse echo testing using the longitudinal wave. You can think about the particles moving, in this case, up and down, compared to a angle beam tester where we're going to be kind of looking more at the shear wave direction side of it. The third type, remember, was a surface wave, and this is used, you use it with a much higher angle. So you can see we have a transducer with an angled block. It starts as a longitudinal wave inside the block, but we have it enter the part at such an angle that that longitudinal wave is going to travel right along the surface. And so, now that longitudinal wave is basically going to create, those ripples, so to speak, on the surface, which is there's going to be a shear component and a longitudinal component. That's going to cause, those ripples that you see is actually the atoms. If you could see it, like on a pond, the atoms are actually kind of making that elliptical or circular motion. But it allows the wave to travel right along the surface. So what you could do, if you don't have access to the bottom of this part, for instance, you can time how long that wave takes to go here. It'll bounce and come back to the probe. So if you were, if you know that a non-damaged area takes, a certain amount of time, if there was a crack right here, the wave would bounce off of that crack rather than the back wall, and you would get a return sooner than what you would get in a non-damaged area. And that would tell you that you have a flaw somewhere or a change in the geometry of the part. A few different examples, kind of how the different probes work. So straight beam with a single element probe is doing a transmit receive function. This is a pulse echo. We send a pulse in, we listen for the echo. You also can have probes where you have a separate driver and pickup element known as a dual element probe. And you can see here they're set at slight angles. So it's still a pulse echo. We're still sending a pulse, listening for an echo. But with two different probes, or two different elements, excuse me, they can be tuned, to better match their function. All the probes we have, everything you're using is going to be a single element probe. Here's that delay line probe. So it's basically a single element probe with a acoustically conductive material in front of it. And so the purpose of this, I mentioned, is that near field area and that initial pulse are going to occur up here inside of this delay line, this T-shaped delay line block. And then everything in the part is going to be far field. So it'll allow you to more, hopefully see things that are near the surface of the part. They won't be obscured by the initial pulse and the near field. The second row there, we've got a through transmission setup. Oftentimes you can use the same probe, the single element probe. Like the probes we have, they can be used for, they can be used as a pulse echo probe. They can also be used, you can hook two of them up to the same tester and use them as a through transmission probe, where it just operates one probe as a transmitter and the other probe as a receiver. There's a type of testing called immersion testing. Rather than directly touching the probe to the part. You put the part and the probe into some kind of a liquid bath. It can be water, it can be oil-based, and that acts as your couplant, but you don't actually have to touch the probe to the part. I've got a video at the end, in fact, that is even a modified version of immersion testing. You don't actually immerse the part, but the probe itself shoots a jet of water out the end of it, and it transmits the sound through that jet of water as a robot moves it around the surface of the part without ever touching the part. And even though you've got moving water that's going to create sound and vibration, it's at different frequencies than what the probe is sending. And so you can filter that out and still be able to test it, even though it makes the noise of like water hitting a surface. And then at the bottom there, we have angle beam testing. Often it's just a single element probe that's set in some kind of, again, another acoustically conductive material, just like the delay line, but at an angle. The last thing here is an array probe. An array probe, just like when we talked about eddy current testing, is multiple transceivers or transmitters and receivers all together in one package. And where those can be handy is we can start to use them to do 2-dimensional and 3-dimensional representations of our part instead of just the the displays that look like this. So straight beam reflective transducers, we're going to see something like this, and we're just going to time how long that signal takes to get from the, that pulse will leave the transducer, travel through the material, and come back to the transducer. And the time it takes, we look at what it is in an unflawed area to the back wall. And if we get an early return, it means there's some kind of a flaw closer to the transducer than the unflawed area. Angle beam testing gets a little bit more complicated because now we're dealing with, we have to know the angles that our sound's going to go. And the biggest thing that we have to be aware of is our angle block here, our acoustically transmitting material, is going to have a different speed of sound and a different sound impedance than the material we're testing most of the time. And so what'll happen there is we'll get a angle of refraction. This is just like if you take, a glass of water and you put something like a pencil or a straw in it, it no longer looks straight, right? You look at a straw going down into a glass of water, and it looks like, visually looking at it, you get refraction taking place where it looks like it's bent. Well, sound does the same thing. When it hits a material at an angle, when it enters a material at an angle, it's actually going to change the path, the angle that it continues at. This one you're not going to have to calculate. I'm not going to make you calculate angle beam testing on any exams. You will need to know how to find the focal point, the near field distance, and you'll need to know how to find the angle of divergence of the sound wave. You do not need to figure out refraction angles. And we're not getting too far into that. Yeah. There's all kinds of array probes. Like they make all kind, like they can do all kinds of weird stuff with them. So probably, but you'd have to look at the specific probe and what it's designed for. Some are to do different frequencies, some are to do different driver pickup arrangements. Some are to go at different angles to look for flaws in different directions. Some have larger coils for doing deep penetration and smaller coils for doing shallow penetration to look at different depths simultaneously. So there's all kinds of options there with array probes. So here's our angle beam testing. We can see our sound path, but if we want to know where the flaw is in the part, that's why we have to understand like the depth, is going to be based on that angle of refraction. We have to use a little bit of trigonometry to figure out, where that, what the distance is, what the distance is along the surface and what the depth is, or the distance from the surface is to our flaw, because it's not going to be a straight down. Angle beam testing is often used on welds. So you can't run your probe directly across the top of a weld because it's not a smooth surface. You wouldn't be able to get a good bond or coupling there. And so we do an angle beam like this to, it's often used to do like check weld penetration. or fill to make sure there aren't voids in the weld and that kind of thing. And so these are used in aerospace, but it's more in the manufacturing side of it versus the in-service. Maybe if you need to do weld crack inspection, you might do something like this. But in all honesty, something that's going to use that is going to be done in a specialty shop. It's not often done out in the field. Okay. Typically in the field, what we're looking at is straight beam pulse echo testing. Here again is that dual element transceiver. The advantage here, two advantages, we can have separate crystals that are tuned to their purpose for transmitting and receiving. The other thing is when you do a pulse echo, right, and that if you're doing a pulse echo like we have here, and that sound's going down and back up again, there is, if your pulses overlap, there is that possibility that the pulse traveling down can interfere with pulses traveling back up, with sound waves traveling back up. And so there is a certain amount of interference that is possible here. In most cases, it's not too big of a deal. But if it is critical, we sometimes need to use a dual element probe so that now our sound paths don't cross one another. But you can see we do have a bit of a refraction angle going on here because they're not perfectly straight up and down. And so, again, they're focused so that they hit each other, but it can affect the way it works.